So this is our last hypothesis test. In this video we're going to look at a hypothesis test for the difference of means with a paired sample. So this sounds like it's going to be very similar to the ones that we did in section 11.1. We did a hypothesis test for the difference of means, but in that case you'll recall, hopefully if you watched that video, that the example we did was testing a blood pressure medication. And we had two different groups of individuals. We had one group that took a placebo and one that took an actual drug. We compared their outcomes to decide whether or not that drug was effective. In that case, the key difference between what we were doing there and what we were doing here is in that case, there were two separate groups of individuals. In this case, when we say that we have a paired sample, we're going to be looking at two samples, but the samples are going to come from the same group of individuals. So a lot of times this will be like a before and after type scenario. You'll take some measurement of a group before they go on a diet and then after a diet to determine the effectiveness of the diet. Or maybe it's to compare different features of a group. I want to compare how much weight I can curl with my left arm compared to with my right arm. And the idea is, in these cases, it makes sense to stick with the same group of individuals for both samples. It doesn't make sense to compare my left arm strength to Arnold Schwarzenegger's right arm strength. It only makes sense to compare my left arm strength to my right arm strength. And that's what the idea is when we talk about a paired sample. So these compare either different features, as I just mentioned, left arm versus right arm strength, of the same individuals, or they measure the same feature of an individual at two different points in time. So before and after, put that in quotes, scenarios. Those are the common types of things that we'll see in this particular case. And it, again, doesn't have to be just for people. We could do one of these for a car. Test how do the front tires on a car wear compared to the rear tires on a vehicle? And again, it would make sense to compare the same vehicle, its front tires, to its rear tires, as opposed to doing the front tires of a little smart car and the rear tires of a giant, 8,000-pound SUV or something like that. So this is the idea. So as before, to do these problems, we need a little bit of new notation. And the notation in this case is going to look a bit different. So let me write these down. The first thing we're going to look at is a D with a little bar over it. And this is the sample mean of the differences in our matched pairs. So this is the sample mean of the differences in all of our matched pairs. And S, with a little subscript of a D, is going to be that sample standard deviation of that same set of the differences in the matched pairs. And lastly, mu sub D will be the thing that we're trying to predict. It's going to be the population mean of the differences in our matched pairs. So here's the three terms that we're going to deal with that are new. And I want to highlight how these differ from some of the other problems that we looked at in Chapter 11. So let me make this totally clear. in 11.1, when we did a hypothesis test for the difference of means, it was that blood pressure medication example, so it wasn't a paired sample. I'll call it an unpaired sample maybe in that case. So two different groups of individuals. We had two of everything. And we don't have two of everything here. We just have one of everything. And the reason was, what we did in that particular case is we took our two groups and we computed the statistics on each of those two groups separately. So we computed the mean blood pressure medication or blood pressure drop in the group that took medication, the mean blood pressure drop of the group that didn't take the medication, and then we computed that one difference. We looked at a single difference of these multiple means. In this case, we're doing things in a different order. We're taking the differences first. So we're taking the before and after difference, or the left arm, right arm difference, for a bunch of individuals. So we have a big long list of differences, and then we compute one single mean of that list of differences. So just as a side note here, to make this totally clear, in 11.1, the previous section that we did, we looked at a single difference of multiple means. So we had, in that case, two means. Right, so we looked at like what we called x bar 1 minus x bar 2, for example. In this section, 11.3, we're looking at a single mean of multiple differences. So, and that's what we're calling this D bar, is, you could think of it as the mean of a bunch of differences, D1, D2, D3. Don't make this scary. I don't want these to look scary. We're not going to ever actually deal individually with D1, D2, D3, and so on. But the idea is, maybe the example we're going to do in a little bit has to do with running times. So basically, we're going to compare a group of runners, how fast they run a mile when they stretch versus without stretching. And so D1 would be the difference for the first runner, and D2 would be the difference for the second runner, and D3 would be the difference for the third runner. We'd compute all these differences in their times to figure out a big long list of differences. Then we compute a single mean. So we, in this case, are computing a mean of a bunch of differences. In 11.1, we computed a difference of multiple means. So a mean of multiple differences, or a difference of multiple means. That is the other big distinction here. So just keep that in mind. If that seems confusing, don't worry about it too much. The whole point is, we're only going to have one value here, because all we've got is this single mean, and it's a mean of a bunch of differences. And that's why we don't have two of everything. We aren't trying to take a difference of these two different quantities. We've already taken a bunch of differences, all of these differences, and we've got this one single mean already computed. We have some conditions for this type of test. They're the same conditions that we've seen in problems that don't involve population proportion. So in all of the ones that involve means, where we need a simple random sample, and we need the sample to be large. So a large sample, meaning we want n to be greater than 30, or we want the population that we're drawing from to be approximately normal. So in this case, or we want d bar, the distribution, let me write it this way. We want, or let's write it this way, the list of differences, let's say it that way, the differences should be approximately normal. And in this case, what they mean by approximately normal means no strong skewness or outliers. That's going to be sufficient to say close enough to a normal distribution. We'll be fine with that. So you may see actual examples of this where they kind of give you a bunch of points and they say, okay, here's all the points, right? Something like this. Does this look like this could follow a normal distribution? And the answer would be yes. Most of the stuff's in the middle. It's not clearly skewed largely one direction or the other, and there's no outliers way at these extremes to either side. So this would be kind of, they'll do a little scatter plot type thing like this and ask if this is close enough to approximately normal. The answer would be yes for that particular picture, so just keep that in mind. Once we've got these conditions met, we can jump into our procedure. And this procedure is the same 6-step procedure we've now done like a million times. So I'm going to go through it a little bit quickly. Step 1 is we state our null and alternate hypothesis. And in this case, h sub 0, h sub 1. H sub 0 is that we think that mu sub d is going to be equal to some value. And this number will often be 0, but it doesn't have to be. And so we'll talk about this when we do an actual example. And h sub 1 will take one of the many forms. This actual population mean may be greater than that value mu 0. It may be, mu 0. It may be less than mu 0, or it may simply be not equal to mu sub 0, or mu naught. So this would be our right-tailed, left-tailed, and two-tailed versions. Step number 2, we define weird. This is the same, I'm just going to say the same as what we've done in all of them that involve normal, all of them that involved t distributions, because you'll notice in our notation, there we go. In our notation, we are using S, the sample standard deviation. So because of this, we are definitely going to be using a t distribution. Whenever you see an S, that goes with a t distribution. So this, step number 2, is the same as basically back in section 9.3 or section 11.1. This is how we're going to be doing it. We're going to define our critical value the same way. So this is where we define weird, and it's going to be the same as what we did back in those cases before. So we'll look at this in more detail when we actually do an example, but just keep in mind these really are all the same. Steps 2, 4, 5, and 6 are all the same in all of these different things. Step number 3 is where we compute our test statistic, and again this formula will look slightly new. It's not too scary. The test statistic is a t-score in this case, remember, because we're dealing with S, and it's going to be, I'm going to take the observed difference, or average difference, so the sample mean of all those differences, minus the value of mu naught, so the assumed value from the null hypothesis, and then I'm going to divide by the standard error. So these are the same 3 things. There's our evidence, here's our null hypothesis value, and this is the standard error. They all take the same form. But really this is very similar to what we used back in section 9.3. The only difference there was this was x bar instead of d bar. And we'll see that even on the calculator. We're going to actually use the same calculator commands we used back here with this, just substituting in this d bar in place of x bar. So we'll see that. And steps 4 and 5 and 6, let me just, to make life easy, these are really all the same. So let's just say same as like 9.3. It's really the exact same thing that we've been doing. We compute the p-value if we need to, we decide if our results are weird, and then we give a conclusion in plain English. So at the end of the day, the procedure for all of these hypothesis tests follow the same 6 steps, and really the highlighted differences are step 1 kind of has some different formats, and step 3 we have different formulas for the test statistic. That's kind of the big differences. Steps 2, 4, 5, and 6 are pretty much the same across all of the ones that involve normal distribution or all the ones that involve a t-distribution. So all the t-distribution ones would kind of be grouped together. Steps 2, 4, 5, and 6 are the same for all the t-distribution ones, and then steps 2, 4, 5, and 6 are the same for all the normal distribution ones as well. So let's jump to an example so that we can kind of talk a little bit in detail about this. So a group of, let's say, 16 randomly selected runners is studied to determine the effects of stretching on their athletic performance. Period. There we go. So this is going to be long, so get ready to write. Let me give us some room because this is going to be a little mini novel that we're writing here. Okay. So on one day, they each run a mile with stretching, and then on a following day, so on one day, they are each timed running 1 mile without stretching. So they don't warm up and stretch beforehand. On another day that we want to be as similar as possible, so similar in conditions like wind, temp, humidity, etc. All those things that could affect athletic performance. We want to control for all of those. So let's keep the second day as much like the first day as possible. They all run a mile after stretching. So they are each timed running 1 mile after stretching. The mean difference in their times. So we take the times of each runner and we compute the average of that big long list of all the differences for all 16 runners. So the mean difference in their times is, let's say, 3 seconds with a standard deviation of 4 seconds. And let's say that this time is measured as their, so the difference is measured, differences are measured as their time that they got when they didn't stretch, so the non-stretching time from that first day, minus the time they got when they did stretch on the second day. Okay, so basically we took a list of differences where we measured their day 1 performance when they didn't stretch minus their day 2 performance when they did stretch, and we got the big long list of differences. We computed the average of that list of differences, and that average wound up being 3 seconds, and the standard deviation of that list of differences was 4 seconds. Okay, let's a few more things. This list of differences, so the differences showed no signs of skewness or outliers. Does stretching improve performance? At a significance level of 0.01. Come on, pen. 0. There we go, 0.01. Okay. Whew. Okay, so there is our question. Let's just go through this together because there's a lot to unpack here before we jump into it. So we've got a group of 16 randomly selected runners, and we're studying them to see whether or not stretching improves their performance. On one day, they all run a mile, we timed them, they didn't stretch. A second day, under similar conditions, they each run a mile, we time them, but it's after they stretch. We compare the times. So we take the difference between, down here, the difference between the day that they didn't stretch minus the times they got on the day that they did stretch, and we find that that average difference turns out to be 3 seconds, with a standard deviation of 4 seconds. This list of difference doesn't show any signs of skewness or outliers. We want to know if stretching improves the performance. So let's go up. Let me do this for a minute. Zoom out a little bit. And go back up here. So a couple of things. Do we meet all the conditions that are required to run a hypothesis test on this? Well, first and foremost, do we have a simple random sample? Yes, we selected the runners randomly, so we're in good shape there. The second one is, do we have a large sample size? And in this case, the answer is no. There's only 16 runners. So we didn't meet the condition of having a large sample. But we did meet this second condition. The difference is if we don't have a large sample, we can still proceed as long as the differences are approximately normal, meaning that they don't show any strong skewness or outliers. And that's why this entire sentence down here was necessary. We needed that sentence to indicate, because we had a small sample size of only 16, that we needed to indicate that at least the results that we got looked approximately normal. So that's why that sentence wound up being necessary. So let me delete that. Okay, so we've taken into account, we've met the conditions, and we've taken into account why this sentence was necessary. The next thing I want to think about is, we're asking if stretching improves performance. So to do this, we need to answer this question, we need to think about what it means to improve performance in the context of running. Okay, so what we did is we found that the difference was measured by taking the time when they didn't stretch minus the time when they did stretch, and we got a number +3 out of that. So what we just did, let me just write this here, maybe erase in a minute. So we took the no stretching time and we subtracted the yes stretching time, and we got a number that on average was positive. It was greater than 0. In fact, it was 3 on average. So if we got a positive number out of this, that means that this number must have been bigger than this number. So this must have been a larger number, and this must have been a smaller number. And remember, what these are referring to is, these are times. So time. Let me write it that way. Don't need that S there. Good enough. Does this even indicate improved performance? So turns out we got a bigger number when they didn't stretch. Is that good or is that bad? Well, in the context of running, we need to think about what that means. If the time when they didn't stretch was a larger number, that means it took them longer to run a mile. If it took them longer to run a mile, it meant they were running more slowly. So again, the question is, what's more impressive? If somebody can run a mile in 10 minutes or if somebody can run a mile in 5 minutes? 5 minutes is faster. So in this case, in the context of running, a smaller number indicates better performance. So just keeping that in mind, this is worse performance, and this is better performance. And so getting a positive number here does indeed indicate improved performance because we took a larger number minus a smaller number. It looks like they were faster when they stretched compared to when they didn't stretch. Hopefully this makes some sense, but this can kind of be a confusing thing. We need to have some sort of background knowledge and background understanding of the context of the problem to make sure that things make sense. The whole question that I'm trying to get at is this number right here, +3, a positive 3 seconds. When we see a number like that for our difference, does that number indicate improved performance or degraded performance? Is that them doing better or worse when they stretched? And we've got to keep that in mind. We need to keep in mind how we define this. We took this difference as being the non-stretching time minus the stretching time, the time without stretching minus the time when they did stretch. And we got a positive number, meaning this number was bigger, this number was smaller, and with that in mind, bigger numbers are worse in the context of running, smaller numbers are better. And so this would indicate that stretching yielded better performance than not stretching. So it looks like that's what the evidence is showing. We just want to decide now if that evidence is strong enough. So this is kind of the idea. This is not really part of the hypothesis test here. This is just us checking the idea of, does our difference of 3 seconds that we found, does it even indicate, is it even evidence of improved performance? And after thinking about what it means, we've concluded yes, positive number does indeed indicate improved performance. Okay, so let's jump into the problem. Step 1, we need to state our null and alternate hypothesis. We found this evidence that stretching improved their performance. We want to know how strong that evidence is. Is it a fluke? So in this case, our null hypothesis and our alternate hypothesis should be as follows. The null hypothesis says, no, I don't think stretching does anything. It doesn't improve performance, right? Again, the word null in null hypothesis, null means nothing or zero. We see zero change, zero improvement. What that would indicate is that the average difference that I find, mu sub d, should be what? If there's no difference between stretching and not stretching, what should the average difference be? It should be 0. So this is kind of the trickiest part of this problem, is figuring out our null and alternate hypothesis. Alternatively, the evidence suggests that the difference is in fact positive, that it's greater than 0. So this indicates basically no difference between stretching and not stretching. And we're going to assume there is no difference and try to figure out, based on that assumption that there is actually really no difference, how likely is that 3 seconds that we found to just be a fluke? Could that have just happened by chance, or is that really unlikely to have happened by chance? And down here, this indicates no. First of all, it's right-tailed, and it indicates improved performance. So stretching helps. That's kind of what that conclusion winds up meaning. I mentioned earlier that this number is often 0. And it's 0 in this case because the question isn't, does stretching help improve their times in running a mile by at least a second or by at least 2 seconds? It just says, does it improve performance at all? So is it better than nothing? And that's why we use a 0 here, that idea of nothing. Here is no difference. Here is some difference better than nothing. Stretching is better than not stretching by a factor of it. Something better than 0. It'll improve your time by more than 0 seconds, essentially. But we could rephrase the question. If the question had said instead, so right here, if this sentence right here, instead of just saying, does stretching improve performance? In fact, let me erase the last part of that. Instead of just saying, does stretching improve performance, like at all, we could say, does stretching improve performance by at least 1 second? And if it said by at least 1 second, then I would put the number 1 here in those two places instead. Or if it said, does it improve performance by at least 2 seconds, I would put the number 2 here, 2 here, and 2 here. So that's kind of the idea. The number that goes there has to do with what question's being asked. If it just says, does it improve performance at all, 0 is kind of our cutoff of at all. If it says by at least a certain amount, by an amount A, we would put whatever that number A is right here, whatever number happens to correspond to that. So hopefully that makes some sense as well. Okay, so let me erase all of this. Hopefully our null and alternate hypothesis makes sense here. Let's do, just to make life easy, let's just do, so up here, let's just use the p-value method. The p-value method in general is the more useful method. I think I put a lot more p-value problems on your homework. And the p-value method is more useful because the p-value itself is a really useful number. Remember, the p-value tells us the probability of getting the results that we actually got. It gives us how unlikely our results are. So for step 2, where we define what we're going to consider weird, that's all we need. I just need the significance level. For doing the p-value method, all I need is alpha, and alpha is 0.01. We're going to consider something weird if it happens less than 1% of the time. Step number 3. Here's where we compute the test statistic, so where we actually look at our evidence. And our evidence says the following. So here's the formula again, just to remind you. It's d bar minus mu 0 over sd over the square root of n. We found an observed difference of 3 seconds minus an assumed difference of 0. This is our number right there that we plug in. There's our, I guess I didn't need to scroll for that. But that's where we're getting that 0 from. That's the mu naught. And we're dividing by 4 over the square root of our sample size, which is 16. And this one we don't even need a calculator for, although you're welcome to use one. The square root of 16, so what number times itself gives you 16, is 4. And 4 divided by 4 is just going to be 1. So this whole denominator is just going to be 1. The numerator is just going to be 3. The whole number we get here is just 3, exactly. And you could do that on a calculator if you have any doubts. So, let me just summarize what we've found so far with our little picture, just to make it totally clear. Here's our picture so far. Here's our curve. And this is the list of all the possible d-bars. We're assuming that the difference is 0. But we found a difference of 3 seconds. And the question is, where does that occur? Well, our cutoff is going to be right here. This is the area that we're going to consider weird, the top 1% of the area. So here's our cutoff of anything that falls over here will be weird. Anything over here is not weird. And we just found that our t-score is 3. So our evidence is at 3. But because I don't know what this t-score is right here, we would only know that if we were doing the critical value method. I'm not sure where 3 falls. I don't know if 3 is like over here or is it over here. So it's going to be close. It's going to be somewhere over there. So the question is, where is t equals 3? And we're going to figure out where it is by finding the area associated with it. So that's going to be our step 4. So now we're going to find the p-value. And again, this is because we're only doing the p-value method. P-value is equal to the area, in this case, to the right of t equals 3. Okay, so how do we do this? Well, because it's a t-distribution, we're going to need to know our degrees of freedom. So we want to find the area to the right of t equals 3 for alpha equals 0.01, and our degrees of freedom is 1 less than the sample size, so 16 minus 1, which is 15. So keep that in mind. Let's take a look at our table, and again, we're using a t-distribution. The only table we're allowed to use is table A3. That is the only one that works for t-distributions. Table A2 is normal distributions only. So I just want just that one. Here we go. So let me move this over to the side here. Move the whole thing over this way. Let's see if I can get this all kind of on the page at once. Okay. So we just figured out our degrees of freedom is 15. So that means this row right here is the only row that I'm allowed to use. And we're trying to find the area associated with the t-score of 3. So our t-value is 3. 3 clearly does not show up in this list of numbers. So going through this, these are all the t-scores, and I don't see 3 on here. It's somewhere between those two numbers. So I need to write those two numbers down. One is 2.947, and the other one is, let's see, 3.286. So my test statistic, the t-score, is between these two numbers. And that means that the area associated with this, which is the p-value, must be between, in fact, let me leave that symbol off for now, between the areas associated with these. And what are the areas associated with these? So going back to here, what is the area associated with this one? Well, I just track back up to the top, and I find that the area associated with this one is 0.005. Oops. Let's go back to black here. 0.005. And for the other one, 3.286, it has an area of 0.0025. 0.0025. And so that's the larger area. The symbols actually go the opposite direction here. The p-value, I don't know exactly what it is, but I know it's between these two areas, these two probabilities. So again, remember, area is the same as probability. So I don't know exactly what the p-value is, but I know it's less than 0.005. So let me delete this while I'm at it. We've got that value now. So is our result weird? Our result is weird. And it's weird because our p-value, even though I don't know it exactly, is less than 0.005, which is definitely less than 0.01, which was our cutoff for weird. It was our significance level. So in this case, the probability of getting the results that we got by chance is less than 0.005. Finding a difference of 3 seconds just by chance, if we assume that that was just due to dumb luck in the sample of runners that we got, and that if you took a different sample of other runners, all the average differences should really be 0. There's really no difference. If there's really no difference between stretching and not stretching, then finding a difference of 3 seconds in our sample is likely to happen less than 0.005 of the time. So less than half a percent of the time. It's very unlikely to have just happened by chance. So what we've concluded is, no, this is not the outcome. Our outcome is indeed over here. We got some number, I don't know exactly what it is, but this p-value right here which is that area under the curve. I don't know exactly what it is, but I know it's less than 0.005, which is definitely less than that number there. So it must be a smaller region. Because this is a smaller area, it must be a smaller region, and our cutoff must be further into the region of wherever the cutoff was for what we considered weird. So hopefully that makes some sense. Okay. So with this in mind, our result is weird. What does that mean we need to do? That means we need to reject the null hypothesis. It's only weird under the assumption that there is no difference between stretching and not stretching. We have just rejected this notion. We have come back and said, no, not the case. Mu sub d is definitely not equal to 0. The evidence very strongly suggests that this is true instead. And what does this mean in plain English? Well, in plain English, this means that stretching helps. So we can either just say the evidence strongly suggests that stretching helps. We don't even need to say to mention the evidence. We could just say stretching improves running performance. Alternatively, you could mention the evidence and say the evidence strongly suggests that stretching improves running performance in these 1 mile runs at least. So that is the idea. If we're doing this on the calculator, I mentioned earlier, this is really exactly the same as what we did back in section 9.3. So we'll hit the stat button, go to our list of tests, and this is just going to be a t-test. So all we're going to do is when it asks for X bar, so let me get into the calculator and get to that page, stat, test, t-test. Here's what it asks for. Let me put them in the correct order. So it asks for mu0, it asks for X bar, it asks for Sx, and what we're going to put, oh, and it asks for n, and then the form of our alternate hypothesis, which in this case was mu greater than mu0. So these are all the things that it asks for. What I want to think about is really saying, okay, this isn't quite what these symbols are going to mean anymore. This is going to play the role of mu sub, well, actually no, that first one is fine. Let me erase all of these. That one's fine. These two are the ones that are going to change. So really, mu sub 0, we put 0 in for that number. But these other two, this is really going to be what we call d bar, and this Sx is really going to be what we call Sd. So just keep in mind, there is no X bar in this problem. We had d bar instead. We're just going to put d bar in place of X bar in the calculator. So our d bar, the average difference, the mean of the differences that we did find was 3 seconds, and our standard deviation excuse me, of those differences was 4 seconds, and our sample size was 16. And so if I plug those in, 0, 3, 4, 16, and pick the appropriate form of the alternate hypothesis, hit calculate, it will spit out that t is equal to 3, exactly as we expected. So this is our step 3, our test statistic. And then it'll actually give us the p-value. So it just calls it p again on here, but the p-value is 0.0044486 ... which does indeed agree. So this number right here should agree with what we found right there. We, using the table, so this was using the table A3, we were able to ballpark it as being less than 0.005, more than 0.0025. Here's the actual number. Indeed, it is less than 0.005 and greater than 0.0025. So again, the calculator just gives us step 3, and right here is step 4. It's up to us to draw the appropriate conclusions from that information. So this is our last hypothesis test, the last section. Go through these on your own a little bit, and I will hopefully have a review up relatively soon where I can, again, try to guide you through how do you pick which approach to take for which type of problem. It'll do a quick review of all the different notation, what all the different symbols mean, because I know it gets very confusing. And so hopefully, if you're still feeling a little foggy on some of this stuff, that video will kind of clear all of this up a little bit and make it easier to kind of organize in your mind which type of approach goes with which type of problem. Good luck.